Welcome. This is Jose Oderman speaking. Today, we'll be continuing with Module 6, where we'll dive into the fascinating world of data analysis for facies modeling. So get ready to discover and learn in a fun and dynamic way. We're diving into depositional environments, which are essential for predicting how facies are distributed in a reservoir. Picture a deep-water submarine fan system. In the axial section near the channels, you have coarser sediments like sands, which are great for storing hydrocarbons due to their high porosity and permeability. Further out, in the off-axial section, you get finer sediments like shales that act as barriers, compartmentalizing the reservoir. By understanding these patterns, we can create accurate facies models, optimize resource extraction, and make smarter decisions in exploration and production. So, let's get ready to model. Welcome and let's get started. The image presents the statistical discrete data analysis available in Petrel, a tool used for modeling geological facies. The key functionalities include facies proportion, vertical facies variation, facies thickness, thickness of individual facies intervals, facies probability, calibration with secondary attributes, discrete variogram, spatial facies continuity, facies proportion, declustering, reducing sampling bias. The data analysis results combined with the conceptual segmentological model can build a more realistic facies model when used in the facies modeling process. This analysis is the first step in facies modeling. You can perform it when an upscale facies property is available. In this image, we observe a thickness histogram for discrete facies types. The histogram illustrates the distribution of thickness for each facies, helping us understand the geometry input for subsequent facies modeling, e.g., object modeling. This analysis ensures that the cell thickness aligns with raw log data. Additionally, discrete statistics provide valuable details like minimum, maximum, mean, and standard deviation for the interval heights, along with the number of cells, offering a deeper understanding of the vertical resolution of the data. The image shows the vertical proportion method in Petrel, used to analyze and adjust the probability distribution of facies in a selected zone, based on the K-layer fractions. The process controls the vertical facies distribution during modeling. The user can edit facies fractions when they don't reflect the expected 3D population. In this example, channel and levee facies are more abundant in the upper layers, while lobe facies dominate the lower layers. Variogram ranges, trends, and probability. In this 3D probability analysis, we're examining the relationship between discrete facies and a continuous secondary property, such as acoustic impedance. This helps guide facies modeling using algorithms like sequential indicator simulation (SDS). At low impedance values, the probabilities of generating channel, levee, and lobe facies are nearly equal. As impedance increases, the likelihood of generating shale facies grows. This process also involves smoothing probabilities and locking other facies to prevent unintentional changes during editing. It's a key QC method for ensuring accuracy and addressing any outliers. Variogram analysis helps compute and model indicator variograms for facies, key for sequential indicator simulation, SDS, and truncated Gaussian simulation. You can model variograms in vertical and horizontal directions, with anisotropy providing insights for object modeling. Start with vertical variograms to define the nugget and model type consistently across directions. Use raw data, remove trends, and apply a larger lag tolerance for smoother results. Omnidirectional variograms, 90-degree tolerance, should be analyzed first. If the omnivariogram lacks structure, directional variograms will likely follow suit. The indicator variogram calculation process involves the following steps. Convert discrete facies data into binary form, setting the facies of interest to 1 and others to 0. Use these binary codes to calculate the semivariance for each lag. Compute a prior distribution function, PDF equals FZ. Calculate the variance as var equals FZ, asterisk 1FZ. Standardize the classical variogram by the same variance formula. This method is essential in modeling spatial continuity for each facies during simulations. The image illustrates how to set the search cone parameters for variogram analysis. It shows the experimental variogram computation table, where you adjust values like lag distance, bandwidth, and tolerance angles to fit your data. The vertical lag distance is based on cell thickness or log sampling, and the lateral lag distance depends on well spacing. Using the first guess button provides an initial setup, but manual adjustments may be required to refine the search cone, ensuring better accuracy for your model. The image illustrates how to set the search cone parameters for variogram analysis. It shows the experimental variogram computation table, where you adjust values like lag distance, bandwidth, and tolerance angles to fit your data. The vertical lag distance is based on cell thickness or log sampling, and the lateral lag distance depends on well spacing. Using the first guess button provides an initial setup, but manual adjustments may be required to refine the search cone, ensuring better accuracy for your model. To make variogram fitting more engaging, 1. Start with the vertical direction where you have more data. Adjust the nugget, sill, and structures using raw logs. Use the Fit Variogram to Regression Curve button to quickly align the model with your experimental data. 2. Lock the nugget and sills once you're satisfied to prevent accidental changes. 3. For the horizontal directions, switch to Simbox mode and repeat the process for both major and minor directions. Unlock and relock nugget and sills as needed, fine-tuning until you achieve the desired model. To continue with fitting the variogram model, 4. Modify the variogram parameters in the variogram model fitting table or directly within the graph for precision. 5. Lock the nugget and sills to prevent changes while adjusting other parameters. 6. For the major horizontal direction, repeat the process using upscaled data in Simbox mode. 7. Similarly, adjust the minor horizontal direction using upscaled data, ensuring the variogram is aligned with your criteria by locking the nugget and sills once satisfied. The declustering process in the image shows how to adjust facies proportions by reducing sampling bias. Here's the process. Select the declustering settings, either 2D or 3D, and choose your target facies. Decide whether to minimize or maximize the proportion based on your known biases. Choose the declustering algorithm, cell or kernel. Then click Estimate to calculate the declustering weights and grid resolution. The weights are applied to the input data to adjust the facies histogram, balancing over or undersampled areas in the reservoir. This image demonstrates how to reduce sampling bias using declustering techniques. By adjusting the settings, you can address facies proportions that are either overestimated or underestimated. Here's a quick guide. 1. Select the target facies and declustering algorithm, cell or kernel. 2. Choose 2D or 3D declustering, depending on well type. 3. Decide to minimize or maximize proportions. Click Estimate to compute the optimal declustering grid resolution, automatically applying weights to correct for bias sampling data. Imagine you're tasked with building a geological map of the underground, and your first step is modeling variograms. You start by creating vertical variograms, which are easier to estimate since you have plenty of well data for this direction. Then, you choose a model that best fits, whether it's spherical, Gaussian, or exponential, to capture the subsurface variability. However, when you move to horizontal variograms, data becomes scarce. This is where your geological intuition kicks in. You leverage secondary data sources that correlate well, filling in gaps and making educated estimates for the horizontal variograms. With careful adjustments, you craft a complete variogram that informs your 3D geological model. providing insights into the hidden layers of rock and sediment deep below the surface. Congratulations! You've now mastered the key concepts needed to perform various advanced analyses. You can confidently run vertical facies proportion analysis, facies thickness analysis, facies probability analysis, variogram analysis, facies proportion declustering. With these skills, you're ready to apply these techniques in real-world scenarios, ensuring more accurate geological models. It's time to put your knowledge into practice and explore the depths of reservoir characterization with confidence. As we conclude this journey, we've gained more than technical expertise. We've unlocked the power of creativity in geological modeling. From building complex facies models to leveraging artificial neural networks and multipoint geostatistics, we combine logic with imagination to visualize the hidden beauty of the subsurface. Now, with these creative tools at your disposal, you're ready to face any challenge. Who spoke to you? Jose Oderman. Be safe, and I look forward to seeing you again soon.